Consider the function lambda from u13 to u13, where lambda of a equals a cubed for all inputs a in u13. Now we've seen that lambda is a group homomorphism, and we have data here that tells us where each element of the domain maps to. And using this data, let's create a visual representation of the homomorphism lambda. So we have all the domain elements U13 here. And for the codomain, not every element of U13 is shown, just those elements that are hit by the function. So we see, for instance, that 1 cubed is 1, 3 cubed is 1, and 9 cubed is 1. In other words, the inputs 1, 3, and 9, let's lump them together because they all map to 1 in the codomain. And likewise, we have, let's see, 2 cubed is 8, 5 cubed is 8, and 6 cubed is 8. So the inputs 2, 5, and 6 right here, they all map to 8 in the codomain. And continuing similarly, we have 4 cubed is 12, 12, and 12. And so now the inputs 4, 10, and 12 all map to 12 in the codomain. And then the remaining 3 inputs all map to 5, 7, 8, and 11. And so we have 7, 8, and 11 mapping to 5 in the codomain. So a couple of remarks here. These 3 input elements all map to the identity element of the codomain. So those 3 form the kernel of lambda. And that's a subgroup of the domain U13. And then in the codomain, we have those 4 elements that are hit by the function, and together they form the image of lambda. So image contains 1, 8, 12, and 5, and that's a subgroup of the codomain U13. Now here's an observation that we've made in the past. A group homomorphism partitions the domain into equal-sized subsets. So the fact that lambda partitions the domain, in other words, these subsets are non-overlapping and they cover all of U13, that's not a big deal. What is a big deal is that those subsets are equal-sized. So in our example here, they each contain 3 elements, as opposed to, say, 4 here, 2 there, 1 here, and 5 there. The fact that those subsets are equal-sized, that's a big deal. And one of the goals of today's lesson is to finally understand why that's true. Now, please pause the video and work on day 25 classwork. And afterwards, we'll review some of the problems and concepts. Once again, we have the homomorphism lambda and its visual representation in front of us. At the top here, we have the kernel K of lambda. These are the 3 elements that map to the identity element of the codomain. And recall that the kernel of a homomorphism is a subgroup of the domain. So we can take this kernel K and compute its cosets. So here is 2K, 4K, and 7K. So we have 4 distinct cosets of the kernel K. And then we notice the following. The cosets of the kernel K partition the domain U13 in the same way that the homomorphism lambda does. And we can verify that by going back to the previous slide and notice that the partition made by lambda is the same as the partition made by the cosets of the kernel K. let's make this news flash a little more precise. So what exactly do we mean when we say that the cosets of the kernel K partition the domain in the same way that lambda does? So we turn to an example. We see that for element 2 in the domain, right there, we have lambda of 2 equals 2 cubed, and that's equal to 8. So lambda maps 2 to 8. Moreover, we notice that every element in that same coset, 2 is in the coset 2k, every element of the coset 2k also map to 8. So if A is an element of 2k, then lambda of A is also 8. So 5 and 6 both map to 8, just like 2 does. Moreover, those are the only elements that map to 8. So only the elements of 2k, that coset, map to 8. So if we have an element such as 10, that's in a different coset, then lambda of 10 does not equal 8. Lambda of 10 is equal to 12. And so we have this claim that if A is not in 2k, then lambda of A does not equal to 8. And so that's the more precise formulation of our newsflash, and we'll state it as a theorem in the next slide. Now here's a general theorem. Let theta from G to H be a group homomorphism with K being its kernel. Let little g be an element of the domain such that theta of G equals little h, where H is an element of the codomain. So let's pause for a moment and take a look at a visual representation of this theorem. We have the domain G here, codomain H. This portion in red, that's the kernel K. And then color-coded, we have the distinct cosets of the kernel K. And we're given that theta of little g is equal to h. So little g gets mapped to little h. Now this condition, in the example that we just looked at, we can think of this as being lambda of 2 equals 8. And we make the following claim. Given an element A of the domain, we have that if A is in the coset GK, so the same coset as our special element little g, then theta of A is also equal to h. In other words, every element of the coset GK also maps to h. On the other hand, if A is not in the coset GK, so let's say little a is right here, then theta of A does not equal to h. In other words, only the elements of the coset GK map to h. Before we discuss the proof of this theorem, here are a couple of conclusions that we can make based on the theorem. First is that this theorem is a more precise way of saying that the cosets of K partition the domain in the same way that theta does. And because of that, we can finally understand why the subsets created by the homomorphism theta are equal sized. And it's because the cosets of the kernel K are all equal sized. And next, we'll discuss the proof of the second part of the theorem. The proof of the first part can be found in chapter 25 of the textbook. And here is the second part of the theorem. We'll let theta from G to H be a group homomorphism with K being its kernel. We'll let little g be an element of the domain such that theta of G is equal to little h. And we must prove that given an element A in the domain, if A is not in the coset GK, then theta of A does not equal to h. Now that's a lot of not not an element of, does not equal. So as we typically do in scenarios like this, let's work with its contrapositive. So instead, we'll prove if theta of A equals H, then A is an element of GK. And we've already identified the hypothesis and the conclusion and written those down as the first step and the last step of our proof. Now, before we fill in the rest of the proof, let's do some scrap work on the side. So we already know that theta of A is equal to H. And we also know from the given information that theta of G is equal to H. So those should come in handy in our proof. And our goal is to show that A is an element of the coset GK. And now let's work backwards. Typically, when we write a proof, we should be going forwards. But in a scrap work, anything goes. So working backwards, if we're going to show that A is an element of the coset GK, that means we're going to end up showing that A looks like G times little k for some element k in the kernel. Now, what does that say about this element little k? Well, if that's going to be in the kernel, then we know that theta of little k is equal to the identity element of the codomain. So let's see if we can isolate that element k. Once again, working backwards. So to get rid of this g, we can multiply both sides of this equation on the left by g inverse. And so we end up with g inverse times A is equal to k. And so that alerts us that we should be working with the element g inverse A. And we wish to show that that element is in the kernel. So our goal is to show that theta of g inverse times A is equal to the identity element of the codomain, because that will tell us that the element g inverse A is in the kernel, which is what we want to show. Now, how do we go about that? Well, we see that theta of g inverse times A, by the property of homomorphism, this is the same as theta of g inverse times theta of A, but theta of g is h, so its inverse is just h inverse, and then theta of A is h, and that's equal to the identity element of the codomain, and therefore we're in business. Now let's turn our scrap work into a complete proof. So we already have the hypothesis right here, and let's also acknowledge that theta of g is equal to h. So moreover, theta of g is equal to h. And now we can compute theta of g inverse times A. Hence, theta of g inverse times A is equal to theta of g inverse times theta of A, and that's equal to h inverse times h, which equals the identity element of the codomain. And thus, we just showed that theta of g inverse times A is equal to the identity of the codomain, and thus we can conclude that g inverse times A is an element of the kernel, namely k. Now let's finish up the proof as we did in the scrapbook here. So we can say let G inverse times A is equal to little k for some little k in the kernel. Then, by multiplying both sides on the left by G, we have A is equal to G times little k, which is an element of the coset GK. And thus we can conclude that A is an element of the coset GK as desired. Let's revisit our homomorphism lambda and its visual representation that's in front of us. Now, there are several groups happening here, but I'd like to focus on a couple of them. One of them is U13 mod k, the quotient group, that contains 4 elements or 4 cosets, namely k, 2k, 4k, and 7k. The other group is the image of lambda, which also contains 4 elements, 1, 8, 12, and 5. So here's a crazy idea. Let's compare those two groups, the quotient group, containing those 4 cosets, and the image of lambda, containing the elements 1, 8, 12, and 5. Now, 4-element groups are small enough that we can build their group tables and see what they look like. So, are we ready? Here we go. And if we stare at them, oh my goodness, those two groups look exactly the same. The reds, the blues, the greens, and the yellow are in the exact same locations in the 2 tables. And therefore, we can say that U13 mod k and the image of lambda are isomorphic groups. Now here's the theorem that generalizes what we just observed in our example. It's called the first isomorphism theorem, which states the following. Let theta from G to H be a group homomorphism with K being its kernel. Then the quotient group G mod K is isomorphic to the image of theta, where the coset GK in the quotient group corresponds to the element theta of G in the image of theta. Once again, this is the generalization of what we just observed with our homomorphism lambda. Now, this one's called the first isomorphism theorem. There's the second isomorphism theorem, and depending on which algebraist you talk to, there's a third isomorphism and a fourth isomorphism theorem as well. But there's a reason why this one is the first isomorphism theorem. In my opinion, this is the most beautiful of them all. And so with that, this is the end of today's lesson, and I will see you next time.